Good evening, Prof, and thank you for this time again that we could present our lectures. And this is the last lecture, assignment 6, the algorithm complexity. And yeah, so we can begin sharing right now. Share screen. Yes. Um, this assignment is quite a theoretical discussion on the various very important algorithms that are used from day to day. And we have insertion sort, the traveling salesman problem. You have sum of 3D values, you have radix and brute force password cracker. Now the last one was a very interesting topic because that's currently used in security systems, NSA. So many security agencies use it to crack massive passwords. It takes millions of years to crack passwords, and these are used in day-to-day life and in very complex programs as well. So we'll go to insertion sort. So if you look at the complexity, the insertion sort is a stable algorithm, which means it doesn't have to change the relative order of elements with equal keys. It's in place, so it requires a constant amount O of 1 of additional memory in space. And also it's online. It can sort a list as it receives it. Its orders O of K of n, K into n, where each element in the input is no more than k places away from the sorted position. So they all have to be kind of in a close group. The time complexity is adaptive. It's efficient for data sets that are already substantially sorted. If they're sorted somehow, it'll be very quick. The usefulness is that it's very efficient for small data sets like other quadratic sorting algorithms. However, when manually sorting, yes, and also when you manually sort cards in a bridge hand, we people automatically implicitly use insertion sort. They don't know that it's insertion sort they're using, but that's what they use implicitly. Now, the traveling salesman problem. Now, this is a well-known problem where a person's salesman starts at one location, he goes around to all the other places, and he returns. So, what's the most efficient way to get back? And also the same problem, a generalized version of this is the traveler purchaser problem, and also the vehicle routing problems. How do we go to a destination and with the minimum time and maybe come back? So that's also a vehicle routing problem. And it's also used in operations research. So there's logistics and planning massive operations. So this is a very generalized algorithm which has multiple purposes. Its orders O power 2 power n square into 2 power n, and this comes under the group of, so as you can see, O power 2 per n square into 2 per n. Um so it won't be super exponential, but it's in midway. And it won't be I'm trying to see if it'll be more than factorial complexity, but it's not fully exponential, so that's okay. And it's not linear either. It's not order of k power n, so it's definitely not as low as this, and it's not super high, so it's in the middle. And it comes under a group of NP complete problems where the worst case running time is a super polynomial, but it's not more than exponentially, with the number of cities. So if the number of cities grows to a very large number, it will not increase exponentially, but it will grow in a super polynomial size. So again, that's not as quick as linear, but it is a polynomial. Yes, it has several applications. Even its purest form is used in planning and logistics and for the manufacture of microchips. If it's slightly modified, it appears in a problem for DNA sequencing. It's also used in astronomy. As astronomers observing many sources, they'll want to minimize time spent moving the telescope between sources. So it's used in astronomy. So this is a very well known and proven algorithm, and which is used in several day-to-day functions. Now we're going to sum of values in a 3D array. Now, this is similar to minimum cost path algorithm used and can be used using dynamic programming. The order is OPA n cube. That's n is the number of elements in the array, but it can also be. See, now we have 3D. I assumed that it was just all of them were of equal size, but if not, it would be O L into M into N. Perfect. If the what do you say um, array size perfect it's not equal. Perfect. Yeah, so if the number of elements is a length m and n are different, yeah, it'll be this. If they're equal, yes, it'll be O n cube. Yeah, I just want to note that. And what is yep, usefulness is just for that. Now, radix sort is a non-comparative sorting algorithm. It avoids distribution into buckets according to their radix. Hold on. Yeah, for elements with more than one significant digit, this bucketing process repeats for each digit while preserving the order of the price step until all the digits have been considered. As a result, it's also called a bucket sort, and it's also called a digital sort. The order is very, very interesting. It's order of n plus b into log b of k, where k is the limit, c is a constant, and if that is where in this case, if k is less than n per c, the complexity becomes smaller, n log p of n. Right, so it is of the order n into log b of n. So we're getting a logarithmic time complexity, which is also not bad. It's not exponential, so we're happy, but it's not really good. It's not as good as the comparison-based algorithms. If you have log n base 2 for every digit, running time appears to be better than quicksort. Okay, for a wide range of numbers, the constant hidden factor is the asymptotic notation for this. A higher for radix and quicksort, and they use hardware caches more effectively. Also, radix sort uses counting sort as a subroutine and the counting sort takes extra space. So we're also talking about space complexity, and by space we mean in the memory buffer in the program ad, execution stack. So how much address memory is it going to take um, for the subroutine? It'll have to compute on itself. The subroutine will have to compute and take up more stack space. Also, radix sort can be applied to data that can be sorted like graphically if the integers, playing cards, punch cards, or mail. So yes, um, if there's an order to the digits, and let's say sorting mail, so we have to sort it by where it should go. Even that also implicitly uses what do you say, radix sort, because you're comparing one with the other, and that's pretty much what we do when we have when the USPS office, when they have a list of when they have a stack of mail, they spread it and they compare one with the other, one with the other, and then they move it. Now let's go to this one, the brute force password cracker. Now this is very interesting because this is used by security agencies or even hackers to break a password. And here we find how exponentially the complexity goes. And the time complexity calculation for 8 characters with no special restrictions is order of 96 to the power 8. Now, I don't know how they got 96, but that's like a standard. So it's power this, which is these many possibilities. But even that can be cracked in few hours. If they have massive GPU units, they'll crack it. Not even CPU, just GPU units. They'll crack this. And if it goes to 10 or order of 96 power 10 results in this, that means it takes 2.28 years to crack such a password. And I came to know if you increase the password length to 14, the brute force time goes to 14 million years. So by just changing a password from 8 to 10 to 14, so why are we even having 10? Let's just have all our passwords at 14 at a minimum. Why are we giving even room for computers to crack this kind of these passwords? Okay, Professor, I thank you for this time, and I thank you for this lovely class, and I hope you have a great day and great fall to, Prof. And I'm very grateful for your time, and I've learned so much, Prof. To learn these algorithms are very important. Graphical theory, especially, it's so practical, and all these systems, all this knowledge is really being utilized. Will be utilized. So thank you once again for this lovely lectures, Professor. Thanks, have a nice day. Bye.